So, hello everyone. Today is the day 11 of linear algebra for AI and ML. I'm your host Hasnul Banda Himel, currently studying at Bragg University in the Department of Computer Science and Engineering. Today is our day 11. Today is 23rd May 2024, and our whole session is fully supported by Global AI Community, Dev Changemakers, NSDC, and TensorFlow User Group Bangladesh. So, what we have learned in the previous sessions and what we are going to learn in today's session. So, on the day 7 or on this Sunday, we learned about the basis, the orthogonal vectors, the orthonormal vectors, and the generic tensor notations. And on the Monday, we learned about tensor transposition, basic tensor arithmetic, tensor reduction, and the dot product. And we learned how we can do this all the calculation or all this kind of mathematical problems, how we can solve this with numpy. And on the day 9 or on the Tuesday, we learned about how we can solve linear systems with substitution and elimination. We learned the methods, we have seen the coding problems, and then we learned about the Frobenius norm. And yesterday, or on our day 10, we learned about affine transformations, eigenvectors, and eigenvalues. We have seen how we can find the affine transformation. We learned about how to plot values in the Cartesian plates. We learned how we can do the using Python, and many more we learned in our previous session or the on day 10. So what we are going to learn today and tomorrow, as tomorrow is our conclusion of our this full 6-day marathon on linear algebra for AI and ML. So in today's session we will be learning about eigen decomposition and applications of eigen decomposition. And tomorrow, on our concluding day of this marathon, 6-day marathon, we will be learning about data compression with SVD, singular value decomposition, and the Moore-Penrose pseudo-inverse. So let's start our today's session. Again, our today's contents will be eigen decomposition and applications of eigen decomposition. So now let's start our today's session. So what is eigen decomposition? Eigen decomposition, or also known as spectral decomposition, is a method in linear algebra where a matrix is decomposed into its eigenvalues and eigenvectors. So in this eigen decomposition, as earlier we learned about LU decomposition, we learned about PLU decomposition, and also we learned about SVD or singular value decomposition. There we learned that we have a matrix, and in the LU decomposition we will be having a lower triangular matrix and an upper triangular matrix. And on the PLU we also have seen that. On the SVD we have also seen that also. So here in the eigen decomposition, the matrix is decomposed into its eigenvalues and its eigenvectors. So how is it represented? Here it is represented as A is equal V lambda V inverse. So here, what is this V? This V is a matrix of eigenvectors of matrix A. And sorry, my bad. This V is matrix of eigenvectors of A, and this lambda is a diagonal matrix where the diagonal elements are the eigenvalues of A. simply said. And what is V inverse? We can say it just by looking at it. It is the inverse of our matrix V. So it is easy, right? So we have, it is represented as A is equal V lambda and V inverse. Our V is matrix of eigenvectors of A. Lambda is a diagonal matrix where the diagonal elements are the eigenvalues of A, and this is the inverse of matrix V. So matrix is singular if and only if any of its eigenvalues are 0. This is important. So matrix is singular if and only if its eigenvalues are 0. So we can find the how to find the, we know how we can find if the matrix is singular or not. We can use the determinant, or yeah, determinant. After using the determinant we can learn if the matrix is singular or not. So on the other point, under specific conditions can be quadratic expressions. Maximum of f of x is equal largest eigenvalue, and minimum of f of x is equal smallest eigenvalue. So now let's do some hands-on code. So yeah, here we have connected our Day-11 Schoolf file. Now, at first, as usual, we will be importing our numpy as np. What we have done from day 7, we're using numpy. And now, here we are defining an array A. It will be our, let me at first clear all the outputs for better understanding. Now, here I have an array in the variable a, and the array is 4, 2 and minus 5, minus 3. When we run this, we will be getting an array of 4, 2 and minus 5, minus 3. And then we are going to define the eigenvalue of a and denote it in lambdas and v variable. So we run this is done, and when we want to see the output of v, it will give me the eigenvalue of v here, 0.70710678 and minus 0.37139068. And on the second row we have minus 0.70710678, and on the last element will be 0.92847669. And now let's find the v inverse. How we can find the v inverse? We will do this np dot linalg dot inv, and we are passing our v, or what is v. V is the eigenvalues of our array a. So we are passing this, and let's do this. Sorry, here let's pass our inv. I have again passed our v. So we are, yeah, so here when we are passing our v inverse, we will be getting 2.3570226, 0.942809004, and on the third element we will be getting 1.79505494, and on the last element we will be getting 1.79505494. So then we will be looking for the lambda. For lambda we will be using another variable lambda. It will be passing np.diag diag and passing the lambdas, or what was our np, or the eigenvalues of a. So when we run this, we will be find the lambda. It will be 2 0 0 minus 1. So we have seen earlier that in our equation In our equation, these all things are in dot product. So how we can do the dot product? To find the dot product, we can pass more than two arguments, right? So to find here, we can do np dot product, np dot dot, find the dot product. We will be passing at first our v, and again we will do another dot product for the rest of 2, comma v inverse. So here we can see that np dot dot, our at first we are passing v, and again we are doing another dot product of lambda and b inverse. When we run this, we will be getting an array of 4 comma 2 and minus 5 comma minus 3. Hello Numan, if you today we are learning about eigen decomposition and the applications of eigen decomposition. If you want me to give, do you want me to give you a quick summary? Hello. Let me continue. So yeah, then we can see that we are getting our the eigen decomposition or fully the eigen decomposition of the a. Here we're np dot dot of v, we're passing our v, and again we're passing doing the dot product of lambda and v inverse. So this was for our regular numbers. Now what will happen when we're working with complex numbers, right? So let me change my screen again. uh, so when we will be dealing with a complex number, it will be given as a is equal q lambda q transpose. And how we are going to do this one, let's again jump to our code. For complex problem, again we got another array a, np dot array 2 comma 1 and 1 comma 2. When we run this one, we will be getting an array of 2 comma 1 and 1 comma 2. And again, just like earlier, how we have got the lambdas and v, now we are getting our lambdas and q in the np.linalg.eigen. Here we have got this. If you want to see what is the output, you can write here like this. It will show us the output. It will be 0.70710,678 and like the other elements, other 3 elements. And when we're finding the lambda, it will be lambda is equal np.diag, and we will be passing our lambdas, or this one, or you can also say we are passing these values here, and our output will be 3001. I have passed again here. So now again we see that we have seen that we have done the dot product, or here we have also seen that this was our equation to find the eigen decomposition, and this was for the normal values, normal numerical digits, and this is for complex values. So now we're doing the dot product of np dot dot of q, and again we can pass more than two arguments here, so we're doing another dot product here on the second argument. Here we're multiplying our lambda with q transpose, and we all know that we can do the q transpose by just writing the qt. If I want to write q dot t, it will give me the transpose of this one. We know how we can find the transpose. Our rows will be columns and the columns will become row, and after finding the dot product it will be 2 comma 1 and 1 comma 2. So here q is an orthogonal matrix. How we can find an orthogonal matrix? The equation for the orthogonal matrix is our q transpose, and q will be equal q multiplied q transpose, and it will be an identity matrix, right? So this can be here, it can be denoted as anyone, like it can be a b c d, till z. You can denote it as anything, as we are denoting our whole matrix here with q, so we're writing it like q. So let's see if q is an orthogonal matrix or not. So after multiplying q with qt, here we're getting a complex value, and after multiplying qt with q, we can see that the value just changed, right? So yeah, this was the eigen decomposition. Now let's move on to our next part of today's session, or the today's concluding part. So what are the applications of eigen decomposition? At first, principal component analysis, or PCA. PCA uses eigen decomposition of the let me use my highlighter or laser pointer. PCA uses eigen decomposition of the covariance matrix to identify the principal components of the data, which are the directions of maximum variance. This reduces the dimensionality of data while preserving as much variance as possible, facilitating visualization and analysis. It also uses in the quantum mechanics. After you learn about AI and ML, you can show some interest in quantum mechanics. In quantum mechanics, the Hamiltonian of a system is often diagonalized through eigen decomposition. The eigenvalues represent the energy levels, and the eigenvectors describe the corresponding quantum states. This aids in solving the Schrodinger equation and understanding systems properties. It is also used in Google's PageRank algorithm. It is also used in vibrational analysis in mechanical systems, also used in image compression. Techniques like singular value decomposition, which will be also learned in tomorrow's session, or something we learned earlier in the matrix part, and pretty few will be learned tomorrow, and related to eigen decomposition, are used in image compression. By retaining only the largest singular values, the essential features of the image are preserved, reducing file size while maintaining the quality. And also we can do the graph theory. What is a graph theory? In graph theory, the adjacency matrix of a graph can be eigen decomposed to analyze graph properties. Eigenvalues can reveal information about graph connectivity, while eigenvectors can identify clusters or communities within the graph. And we can also do the Markov chains. Eigen decomposition of the transposition or transition matrix of a Markov chain helps determine its long-term behavior. The eigenvector associated with the eigenvalue 1 represents the steady-state distribution, providing insights into the equilibrium state of the system. It also helps in control systems. It also helps in facial recognition. Eigenfaces used in facial recognition involves again decomposition of the covariance matrix of facial images. The resulting eigenvectors represent significant features of faces, allowing for efficient and accurate recognition by comparing projected images in a reduced dimensional space. And also it helps in ecomatrices. So that was from my side in today's session. Thank you everyone. If you have any questions, you can ask me.